Welcome, everybody. Thank you once again for joining us today for our weekly astrophysics seminar here at the Institute of Astrophysics. We're delighted to have with us today Dr. Angelos Tsiaras. Angelos did his undergraduate degree at the Aristotle University of Thessaloniki in physics, like many of us here at the Institute of Astrophysics. And then he moved to UCL, University College London, in the UK for his graduate studies, where he obtained his PhD, and where he is right now as a postdoctoral scholar. So Angelos today will talk to us about population studies of exoplanets in the 2020s, and we're very much looking forward to hearing everything about it. So without any further ado, Angela, the floor is yours.
Thank you very much, Vaso. And I would kindly ask you to maybe give me some indication about the time at some point, maybe like 30 minutes or so, because I don't have any way to check the time.
I will give you a 30 minutes notice, 30 minutes left notice, and a 10 minutes left notice.
Thank you. Great. So thank you very much for the invitation. My name is Angelos Tsiaras, and today we're going to talk about exoplanets. But, well, I don't know what you're used to, what you usually hear about exoplanets, but I try to help you get a step beyond at least what we have at the moment, which is discovering planets every day. Of course, this is amazing. And, oh, sorry. Yeah, I need to click. It's amazing how many exoplanets have been found during the last years, especially the last decade. I call it the Exoplanet-boom, because the number has increased dramatically, and today we have more than 4,000 known exoplanets. This has been possible mainly due to space missions, and one of them is called the TESS, is at the moment flying, discovering new exoplanets. So you can see the number here, which is 113 about TESS, but more than 2,500 candidates are still on their way. So I expect this number to grow dramatically over the next few years too. With different colors, you can see different methods of detections. We're not going to talk much about detection methods today, but the two primary ones are the radial velocity and the transits with red and green. You can see that the red one is practically linearly increasing, while the green one is exponentially, because we have more and more methods and more missions using this method to discover new planets. From these 4,000 planets that we have so far, there is a quite wide distribution of characteristics. So here in this diagram, we plot the period versus the mass of the planets discovered. You can see, not all of them, but we can see the main categories. So we can compare the exoplanets in red and blue here with the planets of our solar system. And one thing to notice is that the planets discovered with transits, here are in blue, are quite biased towards shorter periods, because this is detection bias. The transit method is more sensitive to closing planets. But overall, we can separate the exoplanets into three big categories: the hot Jupiters on the upper left part, the cold Jupiters on the upper right part, lower temperature but Jupiter-sized planets, and then the smaller planets, which span from Earth to Neptune, and we call them, actually we used to call them super Earth, and we'll see how things have been evolving recently. We were very happy to see 2 years ago now the Nobel Prize going for being shared to the scientists that discovered the first exoplanet around a main sequence star. Although I have to say that that was not really the first exoplanet ever discovered, but it was the first exoplanet around a main sequence star back in 1995 now. It's been quite a long time. So there has been a variety of missions that have been used to discover or study exoplanets. The first row here is about telescopes that are dedicated to exoplanets. So you can see Corot, Kepler, TESS, and Eclipse. These are current or past. And the first three were about detecting exoplanets. Eclipse is about following up. And at the bottom, you see non-dedicated missions and we will talk about Hubble quite a lot. I have grayed out future missions that we will talk about them later. But with all these instruments, I have made it possible to have this large number of exoplanets until today. The main two methods, as I said, are the transits and our radial velocity measurements. Just very quickly, the transit method is taking advantage of the passage of a planet in front of a star. So we can measure the dip in the star's brightness and infer the presence of the planet, while the radial velocity method follows the movement of the host star, which is also orbiting around the common center of mass between the planet and the star. And then again, we can infer the presence of the planet. In both cases, of course, we are measuring the stellar light and trying to infer the presence of the planet. There are other methods, but I would like to focus on this one because they're important for characterization. Because the transit method can give us the radius of the planet, while the radial velocity method can give us the mass of the planet. Planets that have been discovered with the transit method usually are also monitored with radial velocity, apart from the very faint targets. So when we talk about characterization, we are mainly talking about planets that are transiting, because at the moment, at least, these are the planets that for which we can more easily study further their characteristics.
Angela, may I recommend you turn your
Yes.
camera off, because your sound is breaking up a little bit now and then. So I think it will be.
Yes, I think I need to exit here. Okay. Is it better now?
Yes, I think so. Thank you.
Okay. So to start characterizing the planets, we can start from one of the very, very first things that we can measure about planets, which is the radius. So from the detections that we have so far, and especially those that were achieved using the Kepler spacecraft, which were based on transits, we can have a distribution of the sizes of exoplanets. Now, this diagram here shows the expected number of planets, let's say the frequency in which planets exist in the galaxy as a function of the size of the planet. So we don't really have all these detections here, but if we extrapolate from current detections using, taking into account all the biases, all the observational biases that we have about detecting larger and close-in planets, we can calculate the expected frequency. And that was really a revolution in the later years, that we can see this by model distribution. So we can see two populations of small planets being the most abundant in the galaxy. We used to call all these super Earths. Now there is a tendency to separate them between super Earths in the lower peak and mini Neptunes on the larger peak. But they're definitely way more than Jupiters down here. Now, if we go beyond radius and also talk about mass, we can construct this diagram, which is the mass radius diagram about exoplanets, and which has been used to separate planets into different categories. So terrestrial planets, then we have planets that are expected to be closer to Neptune. That's why they call here Neptunian worlds. And then we go to the Jovian planets and then stars. So here is the limit for the planets. But this is a vague categorization of the planets, and it is a first step characterization. So based on mass and radius, we can have a very initial estimate about the nature of the planet, being terrestrial, Neptune, or Jupiter type planet. If we zoom into the smaller planets now, things may become a bit more complicated. So the large planets like Jupiter, they are probably more they can be modeled more easily. Well, the truth is that we see that the radii are generally much larger than the models, so they are somehow inflated. But this can be explained by different mechanisms. But when it comes to small planets, like here we see planets smaller than 50 Earth masses, we can see that there is, this diagram is quite busy. So the data points are real data, and then you can start, we can start discussing about additional information here. So for example, you can see these contour lines here. They are related to the Fulton gap, the distribution I showed you earlier. So if it's practically a 2D version of it. So the population of small planets is here, while the population of the larger ones is somewhere here. Now the smaller ones are clearly falling onto this line here, the 33% iron, which is an Earth-like model expanded to higher values of mass. So these planets could probably be explained, their size and mass could be explained by a model that looks like the Earth, but it's like bigger. When it comes to larger planets, then things get a bit more complicated because there is a clear degeneracy. Here, the models include some percentage of water, and then we can also start adding hydrogen. So there is a break point here at which we do not know to what extent there is hydrogen in an atmosphere of the planet. And this makes a big difference before reaching Uranus and Neptune here. So this is at the moment at least a gray zone about the nature of exoplanets. And of course, the main reason about this is because we are relying all this, whatever I've told you so far, to the mass and radius. So this is a drawing about two potential structures for a very particular, very famous super Earth. It's called DJ1214b. It was actually one of the very first super Earths that were discovered, if it's not the very first one. So here you see a model with a small rocky interior and a lot of water around it, plus a steam atmosphere, while here you have a much larger rocky planet, well, in terms of percentage, but then you have a small amount of hydrogen and helium on top. So this could create the large size of this planet. So these two are more or less degenerate, and we cannot really separate them only based on the radius and the mass of the planet. Another thing that is important is the history of the planet. And at the moment, one possible explanation about the two populations of super Earths is related to the history of the planet. So slightly bigger, more massive planets are assumed to accrete more gas during their initial stages, from which they then lose some due to the heat coming from the star. However, the initial content was quite big, and they are left with a substantial hydrogen and helium atmosphere, forming mini Neptunes. While second category, we're talking about planets with smaller masses that accreted less gas while forming, and they were left with very little or no atmospheres, forming the smaller group of the two bimodal distribution. So this is what we can get. This is all actually we can get from mass and radius, some estimates. At this point, I cannot help myself showing this to actually try and convince you that mass and radius are not enough. We have the example here in our solar system, Venus and Earth, but two planets with almost identical masses and radii, but two completely different worlds. And you can guess what makes the difference, and this is the atmosphere, of course. In the case of the Earth, we have almost a clear atmosphere, little clouds, but in case of Venus, this whole, this very cloudy atmosphere is capturing all the heat from the planet, and the temperature on the surface of Venus is much, much higher. Same happens for exoplanet. the atmosphere is a key. Without knowledge about the atmosphere, we cannot really start talking about planetary science beyond the solar system, because the atmosphere is the place where we will find hints about outgassing processes, links to the formation of the planet, clouds, so weather, generally speaking, even hints about impact that the planet may have, and also escape processes. So we can see through the atmospheric structure whether the atmosphere is stable or not. So the atmosphere is really the key to go one step beyond and really start studying the planets themselves, not only collecting the statistics for their presence. So I said earlier that the planets that have been discovered through the transit method are, at least at the moment, the best candidates for characterization. And this is because they give us a lot of chances to study their atmospheres. This drawing here shows the star, and just in terms for terminology purposes. So when the planet is in front, we say it's transiting. When the planet goes back, we say it's in eclipse. While during the rest of its orbit, actually the rest of this orbit, we call it the phase curve, if we observe it. Now, when the planet is transiting, you may see this small ring around the planet, and this is the atmosphere. So during the transit, some part of the stellar light is filtered through the planetary atmosphere. And of course, part of the light is absorbed because of the different elements inside the atmosphere of the planet. Although this signal is very, very small. We are talking something like 100 parts per million, or even less. We can go down to 20 parts per million, depending on the size of the atmosphere. Generally speaking, this is quite difficult observation to be made. Sometimes we say that it's equivalent of trying to find the color of the wing of a fly flying in front of a lamp in New York with a telescope with instrument in London. So it's quite a difficult observation to do. So when the planet is transiting, we observe it spectroscopically. So this is a spectrum of the star while the planet is going in front. We split it up into different channels. So to create what we call spectrophotometric light curves. Practically, is not really. For spectroscopists, what we are doing is not really spectroscopy. And we're extracting the transit light curves at different wavelengths. So every color here represents the light curve extracted, let's say, from a different box, going from shorter wavelengths to longer wavelengths at the top. You can see also that the transit shape is changing. This is because of the limb darkening effect, not something that we will discuss here. So after that, we can actually measure the transit depth or the size of the planet, the planet radius, as a function of wavelength. Of course, the planet is not changing from one wavelength to another, but any variations in the size of the planet as a function of wavelength give us a hint about absorption of light at this particular wavelength. So here, for example, you see one of these observations. This is wavelength on the horizontal axis versus RP over R star squared, or transit depth, on the vertical axis, and you can see that the planet size is changing. Now, this is not, as I said, a real change in the size of the planet, but we're talking about water absorption in this case. So what we do is to try and compare the observed signature with databases of known absorption features from different molecules. Here, there is a quite long list of different molecules, but when we're talking about current observations, we're quite limited to this range between 1 and 2 microns. So it's mainly about water, methane, and yeah, maybe some titanium oxide and vanadium oxide. I need to mention that these models here have been calculated through the ExoMol project. So by solving actually the equations of atoms and energy levels. So it's a way combining quantum mechanics with exoplanets. Now, this is not really, well, very high definition image for an exoplanet, but with only these 3 data points, this was actually the first ever water signature detected on an exoplanet. That was a very famous one. It's the 1899733b back in 2007. And you see, we're talking only about 3 data points. So 3 light curves, comparing the results from 3 light curves at 4, 6, and 8 micron with the Spitzer Space Telescope. But it was the beginning. Now, we can also do eclipse spectroscopy. So this is when the planet is going behind the star. So when the planet is going behind the star, we can isolate the star and furthermore, the planet itself. So we can measure directly the light emitted by the planet. Here is a sketch of an emission spectrum from the Earth, where you can see the absorption from carbon dioxide, from water, from ozone. And also you can see the small peak here, which is an indication for the thermal inversion that exists in our atmosphere. The temperature as you go up drops and then at some point starts increasing again. This is called temperature inversion and gives this signature. So apart from finding molecules, when we're talking about eclipse spectroscopy, we can also find information about the structure of the atmosphere. This is an example for a very hot Jupiter. This is WASP 121, where the emission spectrum, now it's not the transit depth as a function of wavelength, now it's the flux, the emission from the planet as a function of wavelength. And we can see this signature again. This is from vanadium oxide oxide and water.
Angela, you have about 30 minutes left.
Well, we can also do eclipse spectroscopy. We can observe the spectrum emitted by the planet as a function of the phase. So as the planet is orbiting around the star. And we can also create 3D maps of these planets using the phase curves. So this is a full phase curve. This is the eclipse when the planet is going behind. This is the transit when the planet is going in front. And here is a 2D map that we can construct based on the shape of these light curves, again, at different wavelengths. I will probably skip. Okay, this is another way to do a 2D map of the planet. And well, this is just one slide on methods that are not using transiting planets. So here we're talking about planets that are not transiting. When the planets have been detected with direct imaging technique, so by hiding the central star, then we can actually take a spectrum directly from the planet. So it's the emission spectrum from the planet, where we can have the different signatures from different molecules and also information about the temperature and the gravity on the planet. And this is again for either transitive or non-transiting planets. And these are observations from high-resolution spectrographs on the Earth, where we try to take advantage of the motion of the planet around the star to detect actually the radial velocity signal of the planet now, not of the star. If anyone has questions, we can discuss about it, but that's beyond the transiting planets. Now, until 2013 or 12, we had very limited detections of atmospheres, and they were mainly made with the Spitzer and the Hubble, but the old instruments on Hubble. And we had very, very few molecular detections, and these were on Jupiter size. So both of these diagrams are about this famous HD 1899733b. There was usually inconsistent results and also some delay between observations and analysis, because all these instruments, both the Spitzer and Hubble, they were actually not made to do this kind of observations. They were general observatories, and actually when they were built, we barely knew that we could detect the atmospheres of exoplanets using them. So the real revolution at the moment is because of Hubble. and the new camera, and not only the new camera, but also a new technique. So the thing is that the Hubble is a very sensitive instrument, and when you get a spectrum, so this is the wavelength axis, the stars that we observe for exoplanet science are so bright that they can practically not be observed for long. So what engineers have done to help the exoplanet field, they've been moving Hubble during observations. So in this way, it's like star trails when we observe from the ground. In this way, we can actually gather more light from the planet, from the star, and increase dramatically our signal to noise ratio when it comes to the transit and the atmosphere of the planet. One slide with my small contribution to all this is that this data were not really, we were not able to process this data with automatic pipelines from Hubble, and I spent my whole PhD doing, creating actually this pipeline for analyzing this kind of data. It's called IRACLIS, and it's an end-to-end automatic software that takes the data, raw images, and gives back the spectrum. So the importance of having dedicated tools and automated is that we can go faster, of course, and analyze more and more planets. At UCL, we have established a new framework practically for doing this whole analysis, starting from the Hubble data, using IRACLIS, which at the moment is the only available dedicated pipeline with minimum human interaction, then using the ExoMol data that I mentioned and our retrieval code, which is called TAUREX, which is actually taking the data, the observations and the theoretical models and put them together to find the best result. I would like to mention that all these tools are actually publicly available on our GitHub page. This is a very important part of our work, is to provide all the tools that we are using and practically making this whole analysis from end-to-end analysis possible to scientists outside UCL as well. So with this framework, we were able for the first time to create a very large catalog of atmospheric signatures from exoplanets with the Hubble Space Telescope. We analyzed about 50 data sets with 30 exoplanets, which was the largest sample ever. And here it's the same diagram again, wavelength and RP over R star, but for about 30 planets. And you can see that they are ranked as a function of the strength of the absorption feature here at the center, and it goes down, and at some point we cannot really discover anymore. So we had 16 clear detections of water vapor in the atmosphere of these planets, which all of them were gaseous giants, giants, Neptunes or Jupiters. One key finding here is that water is actually everywhere. We may have the water in mind as an important molecule, but it's definitely important, but it's not rare. We can find it very easily because it has a very strong absorption feature. And also, generally speaking, if you have a little bit of oxygen in a hydrogen-dominant atmosphere, water is very easily formed. So far has been a good indicator of our detections. And we never stopped to the number 30. More and more observations are coming in. Here is a diagram beyond that. It's a new study where we try actually to correlate the strength of the atmosphere. So this ADI number here is about the strength of the atmospheric signal as a function of the planet radius. And we can see this trend here that, of course, the larger planets are expected to have larger atmospheres, and we can see it. So these are Jupiters, these are Neptunes, or they are following more or less the same trend. But not all planets are like this. We have a very small group of bad planets here for which we cannot really detect an atmosphere. And these are gas giants. So there is no chance that they don't have an atmosphere. So this means that they're probably covered fully by clouds or hazes. Now, when it comes to small planets, Hubble has given us many observations of small planets. GJ 1214b I mentioned, and a few others, and also the TRAPPIST-1 system. I'm plotting here the radius gap so that you can see which ones are above and which ones are below. So these are expected to have some atmospheric signal, while these ones are probably expecting not to have some. But for all these planets here, these ones, they have no signals. So especially for the puffy ones here, this is something that was not really expected. So at the moment is one of the very big mysteries of why we don't see anything on these puffy planets. The first detection that was made on a super Earth was about 55 Cancri, a very curious atmosphere, because we're talking about a planet of 2000 Kelvin, and the spectrum that we found had a hint. So this is the spectrum, again, wavelength and transit depth. And we had a hint for the presence of HCN, hydrogen cyanide, in the atmosphere, which is usually a hint for a carbon-dominated environment, so high carbon to oxygen ratio. Of course, with Hubble, we could not really do much more than that, and we probably wait for James Webb to do some more observations and maybe distinguish between the different cases. I would say that the most highlighted result from our work so far has been the Habitable-zone planet K218b. I say mini Neptune now because this planet has been moving on the mass radius diagram a lot because of improvements in the estimation of the mass. So at the moment it's up here, so it's quite high, it's above the radius gap. And we analyzed the observations from this planet, and we were able to detect with confidence the water absorption feature. So here at 1.4 micron, for a planet that has a temperature of around 300 Kelvin. So we're talking about a habitable zone planet, one that receives similar radiation as the Earth. To give you an idea of how degenerate the problem is with the data we have at least, is that we have 3 different scenarios for this planet. One with water and hydrogen, one with water, hydrogen, and nitrogen, and one with water, hydrogen, and clouds. The different cases are so different that actually the water content can vary from 0.1% to 50, which tells you, yes, there is water, but I have no idea how much water is there. We need definitely much better data, but Hubble has told us so far that, yes, we can detect water on this planet, and this makes it a prime target for the future missions. And more recently, we observed another planet here. It's called LHS 1140b, which is just up below the radius gap. So it's on the regime of super Earth. And also, this is also a habitable zone planet. So in our recent publication, so this is this new planet with it's a habitable zone, rocky world, definitely. However, the data are not so good, as you can see here. We're talking about a very very small, only 2.6 sigma detection of water vapor compared to K218b, which was over 3.5. It's much worse. However, we are very excited to have a potential rocky habitable world with an atmosphere with water out there. And this is definitely something that we would like to follow up with future observations with Hubble or at James Webb and Ariel. But at the moment, this is a very good candidate for habitable atmosphere. Now, as I said, we have many more observatories that will come online. Plato here will be another telescope, actually a group of small telescopes that it will try to detect new planets. And then the next one in the line for ESA is Ariel, which is planned to fly in 2028. But the most important highlight for this year is James Webb Space Telescope. Hopefully it will fly in October, and by next year it will give us the first data. At the moment, we still have HST, and Hopefully it will still be flying for another 2, 3, even 5 years. And the data that it's producing will help us to actually have a first idea again for the atmosphere of a planet, if it exists or not. And with more than 2,000 TESS candidates, I'm sure that there will be many more super Earths, some habitable as well, for which we will be able to observe the atmosphere as far as small planets are concerned. For the large ones, we will continue building a population of current data and trying to understand better their behavior. But yeah, James Webb is a really big telescope here. It will be a 6-mirror telescope, a 5-year mission. A lot of the data will be publicly available. And the advantage is that it will give us a much longer wavelength coverage. So here I only plot something between 0.8 and 5, but in practice, for exoplanets, it will be able to give us up to 12 micron. So useful data up to 12 micron. And this huge wavelength range will help us constrain much better the metallicity and the carbon to oxygen ratio. Here there is a plot showing the comparison in terms of uncertainties for these two parameters from Hubble. So with red is the Hubble data, which are coming from only this small square here, while the blue curve here is the precision we can get with all, actually only with 0.8 to 5 micron with James Webb. This is the difference we're talking about. It's a 3 times larger telescope. And this is from the ERS program. So there will be an early release science program. This is an effort from the whole exoplanet community to observe this planet. It's WASP-33, but it's not mentioned anywhere. And try to get this nice spectrum. Beyond that, as I said, Ariel will fly in 2028. I think now recently we have changed this to 2029. But well, it's still, we have some time until then. Ariel will be a 1-meter telescope with a spectrograph from the visible to infrared. So from 0.5 to almost 8 micron. And the advantage here is that it will be a simultaneous coverage for the whole wavelength range, which is quite important. And with James Webb, we cannot do it. We have to do multiple transits and then combine them to get the whole wavelength coverage. So Ariel will try to observe about 1,000 exoplanets, both rocky and gaseous, to detect their atmospheres and the molecular signal from these atmospheres. So here are some examples of data that we expect to get with Ariel. So this is a hot Jupiter, while this is one of the small Neptunes, the J1214b. Although you see here, we have the spectra are not as impressive as in the case of James Webb. Ariel will be a dedicated telescope. This means that it will dedicate all of the 5 or 7 years that it will be flying to exoplanets. So we can pile up more and more observations. And in the end, if we compare James Webb and Ariel, they can do similar in terms of precision. So, and this is the power of having dedicated missions. At the moment, the mission has been adopted. It was adopted in November by ESA. This means that now at the moment we are in the stage of building the telescope. So it will fly for sure. And since it's dedicated, all the calibrations that are done at the moment are towards achieving stability in the instrument. If you want to observe transits, the key factor is stability. You need to telescope your platform to be stable over a range of, let's say, 10 hours or more, so that you can observe before, during, and after the transit. The questions that we will try to answer with James Webb and Ariel, I think in the next decade, they are quite more closer to the planetary science field, at least as far as I see it. One of the questions that, well, we have some indications at the moment from the data is the famous metallicity, mass metallicity trend. So if we plot the mass of the planet and the metallicity, we can see that there is a trend that as the mass of the planet is increasing, the metallicity drops. This can be seen from the planets in our solar system. Here is Uranus, Neptune, and Jupiter somewhere here, with the idea being that you have more gas and lower fraction of heavy elements. From some preliminary data and based on the water feature, the blue data points, some colleagues have shown here that there is a potential trend also on exoplanets, but with more data and with the quality of the data that we'll get from James Webb and Ariel, we will definitely be able to say whether this trend is real or not. Another thing we can do with better atmospheric studies with James Webb and Ariel is to try and track back the history of the planet. The history of the planet plays a significant role in the final atmosphere of the nature of the planet. So, as we know, planets start from smaller bodies and then they start growing. The question is at which stage they will stop and how much gas they will accrete. We believe that by discovering, actually measuring certain ratios like the carbon to oxygen ratio, and from a current atmosphere, we may be able to track back the place in the planetary system that the planet was formed. Also, we can test theories like where do the super Earths come from and why don't we have a super Earth in our solar system? So super Earths could be smaller planets accreting gas, but they could also be larger planets that they lost their atmospheres, a substantial part of it, and they became super Earths. So all these questions, we will be able to answer them through these atmospheric studies, the detailed atmospheric studies that the new decade will bring us. And I think that this is our holy grail. This is a sketch of a potential HR diagram for planets. So here, this sketch shows the equilibrium temperature on the horizontal axis and the planet mass on the vertical axis. And we can start placing planets onto the different positions. So low temperature planets with a lot of hydrogen and helium, these are definitely the gas giants of our solar system. And when it comes to higher temperatures, then you need more mass to be able to retain this hydrogen and helium envelope. Smaller planets may become what we see as lava worlds, so very hot planets with molten surfaces. And the intermediate planets, which are definitely the most interesting ones, they can either be like Earth, or if they have lower temperatures, they may be like Mars, or if they have higher temperatures, they could be also like Venus. So we don't have many examples at the moment. We have only the solar system planets and maybe a few exoplanets, but definitely we need atmospheric studies to be able to say about the nature of the planet. So like nitrogen dominant atmospheres, or generally speaking, as I said before, the metallicity or the carbon to oxygen ratio. Before closing, yes, very quickly, I'd like to say that in our group, we are promoting a lot open science, and we are dedicated to offer open codes, like the ones I showed you earlier, open databases, ExoMol, and I need to say that Ariel Tier 1 data will be open after just quality checks for everyone in the community. And we also organize citizen science and open research projects, like one called ExoClock and some data challenges. I will show you very quickly. This is all within Ariel. Last year we had, now it's 2 years ago. No, last year, yes. We had a data challenge on machine learning. So this is for people outside our field working with machine learning techniques to try and detrend exoplanet data that are coming from very active stars with spots, because this can disturb our light curves a lot. And we have a very good participation. Over 100 teams worked on the problem to win participation in the ECML, the European Conference of Machine Learning. And then, oh, sorry, a project that I'm very happy about is the ExoClock. This is a global network of telescopes. And I'm very happy about it because it actually started from the Holomon Astronomical Station in Halkidiki. With my colleague Anastasia Kokori, we are coordinating this project, which at the moment has more than 2,000 participants, both amateurs and professionals, but mainly amateurs, from 23 countries around the world. And we're collecting follow-up observations of planets that will be observed by Ariel in 2028, so that from now we know very well their ephemerides. So we know when Ariel should try to observe them. So anyone can participate with a telescope larger than 6 inches, whether you're a professional or amateur astronomer. And yeah, I will leave you here. I think my time is up. Yes. From my perspective, from the data analysis perspective, I think that having population studies in these exciting times of James Webb and Ariel will be possible, but it is a very challenging plan because we need to actually analyze thousands of observations. Exoplanet analysis is really becoming a big data problem, and we definitely need open tools, automatic frameworks, and a lot of follow-up observations. Thank you very much.
Thank you very much, Angelo. Do we have any questions for Angelo? You can either raise your hand or just open your mic. Nick?
Hi, let me open my camera so that you see me, Angelo. Thank you very much for a very interesting talk. We do not have any expertise here on planets except the very little that we get every summer from Paul Callas, who is an affiliated member of the Institute and spends his summers in IRACLIS. So we do hear about exoplanets. So thank you very much. So because of this lack of knowledge, I want to ask you two questions. What do you think will happen in the next few years? Will the effort be in discovering more planets or in analyzing the already existing ones?
Well, this says everything. Actually, they are both happening at the same time because we have TESS, the satellite that is looking for new planets, and its mission has been extended. So it will continue for the next couple of years to detect more planets. And this is, well, while I'm not working on this field, I think that it is necessary because we have not really searched our neighborhood. 1 decade ago, Kepler was a mission to actually tell us whether planets are out there. We were not really sure how abundant planets are. And to answer this question, Kepler looked quite far so that it has chances to find new planets. It turned out that planets are everywhere. So today, the TESS, the new satellite, is doing a whole sky survey from space, but it is sensitive more to nearby stars. So we definitely want to find these planets that are nearby, because the close planets are the ones that we will be able to characterize. We cannot really do this kind of studies for Kepler targets that are very, very faint. So we need to find all the planets, or at least most of the planets that are in our neighborhoods. It's very important. But at the same time, there is a need for going deeper for this planet. So I would say both in this term. Maybe after TESS, the interest will be lower. But yeah, at the moment, we still have a lot of plans to find.
And the second question, if it can be answered, already a Nobel Prize is given. This is a very exciting field, new field. So a second one may be given. And is there something really outstanding that people are looking after seeking possibly a second Nobel in the field?
Well, I don't know, but I think as far as our field is concerned, a big step would be anything related to biosignatures. Any signs that can be related to life will be the next big thing. But well, I'm not optimistic that this will happen now, but in a few decades' time, I think it's will be our holy grail at some point. At the moment, we don't really know what a biosignature is, so we are still debating on which signatures can be considered as biosignatures. And then maybe at some point we will find them.
Okay, thank you.
You're welcome.
We have a question from Yanni.
Hi, Angelos. Let me just turn my camera on.
I cannot hear you very well.
Okay, sorry. Is that better?
Yes, yes.
Okay, so thanks for a great talk. I just wanted to ask you a little bit to comment on your analysis methods. I mean, what are the most challenging parts in the type of analysis that you do in your spectral analysis specifically?
Well, as in many cases, these are the systematics. So far, these instruments that we've been using were not built to do exoplanet science. And as I said, we require precisions that are about 100 parts per million or even less. And usually the systematics are of the order of 1 to 2%. So they are orders of magnitude larger than the signals we tried to retrieve. So removing this systematics has been the most challenging part of the analysis. And well, if we consider Hubble, another thing is about the structure of the data, because if you remember, I showed you that they are not really normal spectra, so they look like these weird boxes, and you have all sorts of geometric distortions and stuff like this that you need to correct. So it's much closer to imaging when you try to correct for these distortions rather than photometry. I don't think I have light curves here, but I could find and show you somewhere one of these. So the systematics are quite strong compared to the signal we're trying to retrieve.
Okay, thanks.
Rafael?
Hello, thank you very much for the interesting talk. I would like to ask, what criteria do you use in order to propose for to target a specific system? Is it light curves or what else can it be?
Well, if you have no idea about the planet, so you don't have any preliminary observations, then you need to calculate the expected atmospheric signal. What goes into this calculation is the mass and radius of the planet. So, okay, I can use this diagram here. So, for example, planets that have lower mass and radius, they have higher density. So they are expected to have atmospheres with small scale heights. While if we go up in the diagram and we're talking about very large planets with low masses, so low density, so high scale height. So a high large value for the scale height, and at the same time a very bright host star are the main driving forces. But once you have some preliminary data, then you can tell, for example, here, these have been observed. For the planets that are at the bottom of this scale, whether while we were expecting some good signal, we did not find any. So, well, I'm sure that we will not target these planets with James Webb because we do not expect to find anything, even though they were very good candidates in the beginning. At the moment, we have some degeneracies between the expected signal and the retrieved signal in the end. And I think this is, well, the most important factor for this is clouds. We do not really know to what extent the atmosphere of the planet is covered by clouds. If clouds are extended, then the signals become smaller and smaller. If the atmosphere is clear and there are no clouds, then we can get stronger signals. So I would say preliminary observations are the most important thing. And this is why in Ariel, I didn't mention it, but in Ariel, we will do a two-step survey. First, we will quickly observe all our targets, about 1,000 planets, and then we will pick those for which we will find a detectable signal and observe them for longer time.
Okay, but the first step, if there is no preliminary knowledge, is this diagram.
Yes, it's this one. So based on the mass radius and the proximity of the target of the host star, the brightness, we can select. I think, well, our plan for Ariel is to select around 2,000 planets, and then do an even better selection of about 1,000. And then, as I said, do preliminary observations and then go deeper as the mission continues.
Okay, thank you very much.
Vasilis has a question.
Yeah, thanks, Angela. It's a great talk. As a non-expert, I had two questions. One is a general one, right? We know that planet migration does play a role in the evolution of any planetary system, in particular planetary systems which have multiple planets, right? So my question is, since right now you are simply collecting, you will be collecting data from systems or exoplanets at a specific time of their life. Is there any feeling as to how transient this may be? That is, if the hot Jupiters, for example, are in a stable state of from a dynamical point of view, of an exoplanet system, or is a transitional state that may not be that relevant to begin with if one wants to do statistics? And the other thing, which is more sort of like technical, you showed the great example between the difference between the Earth and Venus, right? And I presume people have made simulations which would demonstrate up to what distance one would be able to make observations with Ariel and discern the difference between an Earth-like and a Venus-like exoplanet. Is there what would that be if it has been done?
Okay, well, I will start with the first one. So, well, the migration, I'm not an expert in dynamics, but I assume that the migration phase is quite short compared to the whole life of the system. But in any case, what we're trying to do from now, at least for Ariel, is to also try get the best estimates for the age of the systems that we're going to observe. Ideally, we would like to have a range of ages. So even starting from planets that are very new, newly born, going towards older systems. But well, my feeling is that most of the systems that we're going to observe are old enough. So we're talking about systems after migration. What the connection? Well, what we're trying to do is to try to connect the current, let's say, the current composition of the atmosphere to maybe the composition of the protoplanetary disk, and maybe try to detect the initial position of the planet. This is an idea that exists for some years now, but yeah, it is not so clear yet how this will be done. But it's an avenue that many scientists are exploring, and it's quite interesting one to be able to go back in time and see where the planet came from. Concerning planets like Venus and Earth, well, there are quite important differences as far as Earth and Venus are concerned. Although Ariel will not be able to go that deep, so small planets, but maybe one of the future instruments. I think the most important difference is the presence of oxygen and ozone in the atmosphere of Earth. And speaking, I think also the difference in the methane component on Earth is quite different one compared to Venus. But yeah.
But at what distance can we detect those? I mean, how?
What do you mean distance?
Like if you have an exoplanet of our galaxy, which is a kiloparsec away, can you
Distance
see?
from us.
From us, yeah. What is the volume
Okay.
of exoplanets?
Oh.
You see what I mean? You know, because of the
yeah.
absorption line measurements are sensitive, right? Are much easier than emission-like detections.
So well, one thing is how far exoplanets are, and I think most of the exoplanets that we have are within 1,000 light years. We cannot really go much further. And as far as characterization is concerned, I would say a few hundreds of light years, but not more than that.
Okay. So
our best chance is to actually not really get sun-like stars, but at the moment there is a big focus on smaller stars, M dwarfs, because in this case the radii ratio between the planet and the star is quite larger. As an Earth, like the TRAPPIST-1 system, an Earth-like planet around an M dwarf would give the same signal as a Jupiter planet around the sun-like star.
I see Yanis actually mentioned a few hundred parsecs. So basically you are sampling the nearby thin disk. That's what you are doing in the galaxy. You don't go a bit further. Okay, thank you.
Yep, very good.
Because that has to do with the age as well, right? That's what I was trying to, since we have the puffing. Yeah. Okay. Thank you.
Yeah, very good point about microlensing too, but unfortunately we cannot really follow up microlensing planets.
Alexis has a question.
Yes. Hello, Yanni. Hello, Angele. Congratulations for your informative talk. I would like to ask a more technical question. Can you go to your 20th slides, please?
Which one?
20th.
This one?
20th. Yes, exactly. I see here, this is a phase curve of transit and eclipse of an exoplanet, but I can see that there is a clear asymmetry before and after the eclipse.
Yep.
So why is this happening?
This is due to the distribution of the flux distribution of temperature over the planetary surface. So if you look on the map on the right-hand side, the temperature of the phase that we see is not uniform. Usually there is a hotter region, a hot spot as it's called, and also this hot spot is not just at the center. It's also really there is a hot spot shift, as we call it, because of the superrotation of the atmosphere. So the peak is it could be if the eclipse is happening at the same time as the peak, this means that we don't have any hot spot shift. The hot spot is just under the substellar point. But if the peak is a bit left or right, then it means that the atmosphere is actually moving the hot spot towards different latitudes.
Okay, so
longitudes. Sorry.
How
longitudes.
difficult is to distinguish this effect you described with a star spot?
Star spots?
Yeah.
Okay.
These asymmetries are typical for star spots also. And not due to the planet itself.
Well, but the variations due to star spots, I assume they have a different period compared to the period of the planet. So I never thought about why would we confuse it between the two of them.
Okay.
Yeah. And also we're looking at wavelengths that are quite far in the infrared, so I don't think that the signature from spots would be quite strong here.
Okay, thank you.
Yanis has another question.
Yes, thanks. I think I'd like you to speculate on something again. Sorry for me. Right, I think if
you do that a lot. No?
Yeah, if you go to the beginning of your slides, right, you saw the distribution
This
with
one.
orbital radii, sorry, with the orbital period or distance, was it in AU? I think further up or further
This
down,
one.
is it? Yes, that's the one. So we have the
this one.
period. So the vast majority,
Mhm.
and this is a point that is usually not appreciated. Everything that we know about planets is basically based on planets within 1 or maybe 2 AU. These are where all the Kepler planets are, where all the radial velocity planets are. Okay, so something interesting happens further out once water turns to ice beyond the snow line. Okay, but as Angelos shows there, it's really hard to find these planets. And I was wondering, when do you expect that we can actually follow up on some planets, that have 3 or 4 AU? Will you be able to, within your lifetime, actually make any observations of planets that are further out? Because the distributions are going to be different. They have much more material there available to grow larger. This is where we believe that this is the birthplace, basically, of large planets, of gas giants.
This is an excellent question, actually. Well, I think at the first stage it will come to it breaks down to how long you need to wait to discover such planets. So if we're talking about transits, and there is one transit every year or even worse, then we will have to wait for decades, definitely, to discover them first. I think characterization, after discovering characterization, if a planet has some good characteristics, and we're talking about gaseous planets mainly, then there is that's not a really problem, because when the planet is transiting, you just go after this particular transit. But it's very difficult to discover them. I think that's the main point. And missions like TESS should continue for much longer periods. And when we will find, if it continues, if we have a second TESS, why not? Seems quite successful so far. Then yes, why not? Nearby stars with long period planets, I don't think that's very difficult in terms of characterization, but we need to find them first. Now, there is a small category of planets which are far away, and these are the directly imaged ones. I'm not an expert on talking about them, but they have this difference because they are usually young planets. So they may not really be representative of all the population. So I would say a few decades, yeah, definitely.
Okay, thanks.
Okay, if there are not any more questions for Angelo, let us all thank him very, very much again for this very interesting talk. And we're very much looking forward to the opportunity to actually having you here in person in Crete.
Looking forward to visit Crete too.
Yes. Thank you, Angelo.
Thank you very much, everyone.
Bye, everybody.